Let us focus now on drag force closures. We want to start with the question, what is the challenge when predicting drag forces? Therefore, let us consider a situation like this. We have a relatively dense ensemble of particles that is submerged in the fluid, for example, water or a gas. When we apply the discrete element method, we are almost always considering relatively dense systems. The reason for this is simple. One would simply not apply the discrete element method to a dilute system where particle collisions are very infrequent and can be modeled much more efficiently with other methods. But this is a different story. In short, if we want to model drag forces in the context of the discrete element method, we are always interested on a dense suspension, and we are totally not interested in the force acting on a single particle. This is very important, and you will see this later. The second point is, due to the nature of the physics of flow in these dense suspensions, we might experience a wide range of Reynolds numbers, let's say ranging from 0.001 to 1000. To sum up, we are interested in the force on a single particle, however, in a dense suspension, so surrounded by many other particles. The approach to attack this challenge is as follows. We're going to start with the so-called Stokes drag force. This is the drag force on a single particle at very low velocity, at very low Reynolds number. You will see the definition of the Reynolds number in a second. The beautiful thing about Stokes drag force is that it can be analytically derived from the so-called Navier-Stokes equation, which you have learned typically in a fluid mechanics course. Of course, if you're writing here the U fluid, we always mean the fluid particle relative speed. So if the fluid has a certain absolute velocity, we must subtract the particle velocity from that to find the fluid particle relative speed. The next step in our chain of thoughts is that the fluid speed might increase, leading to substantially higher Reynolds numbers. The Reynolds number is defined here and consists of the U fluid, so the magnitude of the fluid particle relative speed, the particle diameter, the density of the fluid, and the fluid's dynamic viscosity. In such a situation, we find that the drag force is the Stokes drag force multiplied by a prefactor that is larger than 1. So the drag force increases with the Reynolds number if we would fix the fluid velocity. A very simple correction function for this effect is this so-called Schiller-Naumann drag closure. The next step in our chain of thoughts is to think about the superficial velocity effect. The superficial velocity is nothing else as the fluid speed that would be measured in the system if there would be no particles. So the superficial velocity is lower than the actual fluid velocity. What we're going to do is that we define our drag correction now based on the agreement that U fluid is the superficial velocity in our calculation. So F drag is the Stokes drag force based on the definition of the superficial velocity multiplied by a correction function taking into account the effect of the neighboring particles. The effect of the neighboring particles is simply expressed here by the particle volume fraction. We also go back and consider now zero Reynolds number. Of course, it's obvious that not the superficial velocity is felt by the particles, but the true mean fluid velocity. The true fluid mean velocity, here U fluid in these brackets, is related to the superficial velocity by this function here. So if you put this into the definition of the Stokes drag force law, you will find that this correction function must be proportional to 1 over 1 minus phi p. So in other words, if phi p is close to 0, the correction function is 1. But if phi p is increasing, then this term is decreasing and the correction goes up. Please note that for the Reynolds number, we keep on using the superficial velocity. So this is the superficial velocity. So in the definition of the Reynolds number, you always see this 1 minus phi p. And the reason for this is simply that we would like to keep the superficial velocity in our definition of the Reynolds number. We can now start off thinking of correlations to describe this function f of the particle volume fraction. In order to do that, people have started very early to think about the drag force, and the famous correlation is that of Kármán-Kozeny. The problem with that is, and you see it already here, if phi p approaches 0, the correction function is also approaching 0. So for the dilute limit, this correlation is not suitable, and one can only use it for relatively high particle volume fraction larger than 0.5. The next evolution stage was to think of the limit in case of low particle volume fractions, and here the correlation of Kim and Russell is important. You see that this suggested correction for the superficial velocity was here not taken into account, but we will see that this early correlation agrees surprisingly well for the range of phi p 0 to 0.1 with currently used correlations. The next step was to then fit detailed simulation data with this correction function f. The work of Van der Heuve, Beetstra and Kuipers in 2005 is a very significant work. This correlation is suitable for a very wide range of particle volume fractions. If we look now at this chart here, where we plot the correction function f multiplied by 1 minus phi p squared, so this is here introduced, and the reason for that is that the famous Kármán-Kozeny correlation would then give a straight line. If we plot this quantity versus the particle volume fraction, we will see that the Van der Heuve Beetstra-Kuipers correlation does excellent work. It also agrees with recent very detailed simulation data, which is not shown in this graph. The Kim and Russell correlation does a good job for low particle volume fractions. And again, be very careful with the Kármán-Kozeny correlation for phi p values less than 0.5. What you also should note is that there's an extremely strong increase of the drag force at the same superficial speed as we already announced. If we look, for example, here at the particle volume fraction of 0.5, we find that this f multiplied by 1 minus phi p squared is in the order of 5. And if we now calculate this term here, you will see this is 0.5. And it sums up that this f function, so this correction function, has a value of 20. And even more extreme, if you go into particle volume fraction of 0.6, you see that this term is roughly 6. And again, please note that if we calculate this term here, for this case of phi p 0.6, it is 0.16. So if we then solve for f, we arrive at a 37.5 times higher drag force at the same superficial speed as into the dilute limit. This is really significant. The next steps are rather obvious. We want to extend to higher Reynolds number, and here we have different choices. We can postulate an equation like this, that we again focus on the low particle concentration limit, and then we can make correlations for this exponent beta here. Or what we can also do is we can decompose essentially this correction function f into a part that depends only on the particle volume fraction. We have seen that correlation already on the past slide, and a second term g naught here, which then models the effect of the Reynolds number. Unfortunately, we have to also consider here the effect of the particle volume fraction, so it leads to a little bit more complex term. However, if you look into the citations of this extremely often used work of Bedstra et al., you will find beautiful agreement with very detailed simulation data. We now already approach the end of our chapter on the drag force. In the practical application of these drag force closures, we have a formulation like this. The drag force on a particle is proportional to the particle volume, this drag coefficient here, or friction coefficient as it's sometimes called, and the fluid particle relative speed. This is also what we have discussed already. Please note that this UF average is not the superficial velocity, and we must take into account this by using this factor here. So here you see also this drag correction function f, and this term essentially comes from the Stokes drag closure. What needs to be said is that this is the pure drag force. There is also another important group of fluid-particle interaction forces which is relatively easy to be taken into account, and this is the so-called pressure gradient force. The pressure gradient force, in the absence of any other forces, can be calculated out of this drag force. That's it already for this unit. There is much more to be said about the drag force. Unfortunately, we don't have time for this. I hope you enjoyed it. See you next time.